completed the whole of things. Just will discuss a few quick problems and probably put an end to all this today. Suppose I have a circle here. Let me call this A. I have another circle, shell. These are all shells. Okay, suppose this is A, this is B. And at the center I have Q. Here I have minus 2Q. Here I have 3Q. So questions to you. What are questions to you at point A, B, and C? Find the potential. At points A, B, and C, find the potential. Yeah, can you work it out? This is a fairly simple, straightforward question. So what we would have done is we should have done this A. Total charge inside is 3Q minus 2Q. Q plus Q is 2Q. So 1 by 4 pi epsilon naught 2Q by, suppose this is A and this is B. Suppose this is B. So by B. So that will be the potential of A. Okay. Then potential of B would be 1 by 4 pi epsilon naught 3Q by B minus here 2QQ. So the net charge is Q 1 by 4 pi epsilon naught Q by A. If you go to point C, the potential at C will become equal to 1 by 4 pi epsilon naught 3Q by B minus 1 by 4 pi epsilon naught 2Q by A plus 1 by 4 pi epsilon naught some Q by whatever that radius is. Suppose it is C, so it is Q by C. So this is how I can find out. Okay. Now suppose I somehow earth the middle sphere. I have earthed the central sphere. So if I earth the central sphere, what will happen is the potential of the central sphere will become equal to 0. So what will happen is I will go to a different color. So I'll get VB dashed is equal to 1 by 4 pi epsilon naught. I'll take that common 3Q by B minus new charge on that. So Q dashed by A plus Q by A. That is the potential due to this sphere on this charge. Now this is equal to 0. So now I can rearrange, get the value of Q dash, and from there I can find out how much charge has gone in and how much charge has come out. Okay. So I hope this one all of you will understand. Okay. So if you can make notes. Yeah, make notes. Just give me a minute. Okay, so if you are getting it, then let's go to another question. Now there's a plate here. There is a plate here. And there's a plate here. Suppose this is having charge 2Q. This is earthed. Okay, no charge on this. Suppose this distance here is 2D. This distance here is D. this has a charge, suppose it has a charge Q, or okay, there is no charge here, there is no charge here also, but suppose these two are connected by a potential V. Now the question is, how much charge will appear? How much charge will appear on each plate? Yeah, so try to work it out. How much charge? There is no charge here, there is no charge here. This distance here is 2d, this distance here is d, and there is a potential source V. Now the question is, how much charge will appear on each of the plates? Okay, so quickly work on that, then I will move on. Okay, so if you all have worked it out, great. If you all have not worked it out, no problem, I will help you out. So the way you can go ahead with this kind of a question is this, that okay, so see, suppose the charge on this is Q. Suppose the charge on this is Q. The charge here will be minus Q. Then if the charge here is minus Q, then the charge on this side will become plus Q, because this is neutral. This is a neutral. Yeah, so I think something is wrong with the question itself. Something is wrong. Okay, sorry, I'll give you another question that you guys work out and see if anybody can get it. There is a charge here, a plate here, there's a plate here, there's a plate here. Suppose this is given a negative charge. Now the question is, what is the charge on each plate? Now the question is, suppose this is plate A, this is plate B, this is plate C. What is the charge on each plate? So how will you go ahead with this? So the way we go ahead with this is this, that look, this is, suppose the charge on this side is Q1. The charge on this side will be minus Q1. The charge on this side will be minus Q2. This side will be plus Q2. Now, because these are all connected, the potential difference here will be the same as the potential difference here. Okay. So capacitance, so there is one capacitor here C1, there's another capacitor here C2. Now C1 is equal to epsilon naught A by D. Clearly the distance is double. This distance here is 2D and this distance here is D. So C1 is epsilon naught A by 2D, while C2 is equal to epsilon naught A by D. So what it will mean is that 2 times C1 is equal to C2. This is what it will mean. Okay, so this is what it will mean. So if this potential here is V, then the potential, yeah, so we can calculate first that on the outer plate the charge will be 0. On this plate also the charge will be 0. So Q1 is equal to C into V. So C is equal to epsilon naught A by 2D into V. That is Q1. Q2 will become equal to epsilon naught A by D into V. So this is going to be Q1, this is going to be Q2, and on plate B, the net charge will become equal to by 2D into V. So that will become equal to 3 epsilon naught A by 4D into V. Basically on Q2, the charge will become equal to the sum of these two. So sum of these two, no, I am making an error. It is 3 by 2, 3 by 2. It's going to become the sum of these two. So sum of these two will become 3 epsilon naught A by 2D into V. So this will be the charge on each of the plates. Okay, so now suppose I name these plates 1, 2, 3, 4, 5, and 6. Can you find out what is the potential difference between say 2 and 5? What is the potential difference between 2 and 5? So you will see that the potential difference, both are connected to the positive terminal. So because both are connected to the positive terminal, both of them will be at the same potential. So the potential between 2 and 5 will be 0. Now potential difference between 2 and 3, potential difference between 2 and 3 will be equal to V. Because one is connected to the positive terminal, the other is connected to the negative terminal. So basically this is how you work with it. So these are certain types of questions which we have not done before, which we should do. Yeah, so that is it. There is one more I want to work with you all. Here is a question. There is a capacitance here, there is a capacitance here. Let this be 2 microfarad, let this be 4 microfarad. There is a capacitor here, 3 microfarad. There is a capacitor here, 6 microfarad. And suppose this whole thing is connected to something which is like 6 microfarad. So my question is, what is the charge on each plate? What is the charge on each plate? See these, I will try to work this out for you. Just see if you are able to appreciate what I am trying to say. This is not 6 mu F, this is 6 volt. Okay, first thing is, suppose the potential here is V1, the potential here is V2. Do you understand that V1 plus V2 is going to be equal to 6? V1 plus V2 will be equal to this external potential 6. Then also understand that the charge on this is equal to the charge on this because they are series connection. Yeah. Now because C is equal to Q by V, I can say that C1 V1 is equal to C2 V2. Q on this will be the same. So from there, can I say V1 by V2 will become equal to C2 by C1. So V1 by V2 will become equal to C2 by C1. So do you understand that the potential here will be 4 volts and the potential here will be 2 volts? Why? Because I have to divide it in the ratio 2:1. So I have to divide it in the ratio 2:1. So it is 4 volts here, 2 volts here. So if it is 4 volts here, 2 volts here, now Q is equal to CV. So I can now find out what is the charge on each of them. Charge on each of them will be 12 microcoulomb. So charge on each of them will become 12 microcoulomb. Yeah. Now, by the same logic, do you see that in this case also, the potential difference between these two will also be in the ratio 2:1. So here also it will become 4 volts and here also it will become 2 volts. So the charge on this will now become how much? 8 microfarad. So the charge on the upper one is 8 microfarad. Charge on the lower one is 18 how much? 4 into 3, 12 microfarad. Do you understand? Do you understand that V1 is equal to this? Suppose this one I'll call it as V1 dashed. So V1 dashed and V2 is equal to V2 dashed. This is equal to 4 volts and this is equal to 2 volts. See, at a given point, the potential will be the same. So if I'm going like this and coming back, the drop in potential, when I go from plus to minus, there is drop in potential. So drop in potential in a closed loop, drop in potential must be equal to gain, because a particular point will have a standard potential, whatever it is. So if I go like this, so here positive to negative drop, positive to negative drop, but here I'm going from negative to positive gain. So this drop must be equal to gain. So that's what we are saying, 4 plus 2 is equal to 6. Okay, if you understand this, do you understand that this point here called A and this point here called B are at the same potential? Because when I go from here to here, there is a drop in 4 volts here. When I go from here to here also, there's a drop. So if I connect A and B, what is going to happen? Nothing is going to happen. They both are at the same potential. So if there is a capacitor here, that capacitor will not have any charge. So between two equipotential points, if a capacitor is connected between two equipotential points, if a capacitor is connected, there will be no charge on it. So having it or not having it is of no use. I mean, it's of no concern. So such a circuit is to be identified. How do you identify such a circuit? See, this was 4 microfarad, this was 8 microfarad, this was 3 microfarad, and this was 6 microfarad. This was 2 microfarad and 4 microfarad. So in all these cases, here it will be 4 volt, 2 volt, 4 volt, 2 volt, 4 volt, 2 volt. How do I know? In all these cases, the ratio is 2:1, 2:1, 2:1. Do you understand this? That means this point and this point will be at the same potential. So if you connect these two, what will happen to that wire? Nothing will happen on that wire, because these two are at the same potential. If you connect a capacitor between the two capacitors, what will happen? Nothing will happen. Such a circuit is basically referred to as a Wheatstone bridge circuit. Wheatstone bridge circuit. Okay, in such a circuit, this point and this point are at the same potential, and if they are at the same potential, this capacitor can be moved. So suppose this is 2, 4, 3, 6, and this is 3 microfarad. What is the effective capacitance of this system? To find out the effective capacitance of this system, you can safely remove this. This ratio is what? 1:2. This ratio is what? 1:2. So whenever you have something where the ratios are the same, this capacitor can be removed. This is not same as the 4 being on this side and the 2 being on this side. That is different. Okay, so this can be done only when the ratios are the same. Now the central capacitor can be removed. So now these two are in series. So 4 plus 2, 4 into 2 by 4 plus 2. So that will become 8 by 6. So that is 4 by 3. Here also it is the same thing. 6 into 3 by 6 plus 3. So that will be 2. So now these two are in series. So 2 plus 4 by 3 will make it 10 by 3. So with this capacitor or without this capacitor, the effective capacitance of this circuit is 10 by 3 mu f. Okay, can you please make a note of it? I will wait. I will show you the slide. Make notes. I will wait for 1 full minute. Okay, yeah. So I can ask you, suppose this is C1, C2, C1, C2. What is the effective capacitance of this? We can find out series, parallel. In between, suppose I add a capacitor. Now what will be the effective capacitance? Same thing. Then if I connect these two, then what will be the capacitance? So this is C1, C2. So now this is to be connected. So these two are in parallel. Now these two are in parallel. Okay, and then those two are in series. So that's how you will do it. Okay, so if this ratio here is equal to this ratio here, any capacitor here can simply be removed. It will not affect the effective capacitance. Okay, so I repeat, this is what is referred to as a Wheatstone bridge. So can you find out the effective capacitance of this? What is the effective capacitance of this? All are C. Very simple. You will say it is equal to C by 3. Now suppose I'm connecting these two. Now what is the effective capacitance? Now what is the effective capacitance? So now I have to draw an equivalent circuit and work it out. So I have 1, 3, 4, 5, 6. So if you see that this 1, 4 and 5 are connected to the same wire. So 1, 4 and 5 are connected to the same wire. 1, 4, 5 are connected to the same wire. Then I have 2, 3 and 6. So I have 2 is next to 1. Then 3 and 6 are again connected to the same wire. So now what is the effective capacitance? 3C. Do you understand this? Then I have this, I have this, I have this. I have this connected here. I have this connected here. What is the effective capacitance? All are C's. All are C. Same, similar capacitors. Okay. So what will happen here? Again, I'll name them 1, 2, 3, 4, 5, 6, 7, 8, and 9 and 10. So if I see plate number 1 and 7 are the same, connected to the same point. So I have plate number 1 and plate number 7 connected to the same point. Okay. And on the other side, I have 8, 4, and 5 connected to the same plates. So I have so 8 is here, then 8 is here, this is 7, this is 1, 8, then 4. So I have taken 4 also, then I have taken 5 also. So 8, 5. Then the other side of 5 is 6. So this is 6. 6 goes 6 and 10 is connected to the same plate. Then plates next to 1 is 2. I have 2. Then I have plate 3. Then I have plate 3 here. So this is 4. Suppose I have 8, 4, and 5. So here I have 3. So I have this, and I have the next one, that is 9 connected, 9. Then I have 10 and 6 connected. So this is the diagram. So this is C, this is C, this is C, this is C, and this is also C. Now do you see that this ratio is equal to this ratio? So if this ratio is equal to this ratio, this capacitor can simply be removed. So I can simply remove this capacitor. Now when I remove this capacitor, what I'm seeing here, these two will be in series. These two will be in series. So that will become C by 2. This will become C by 2. Then these two are in parallel. So the net will become C. So this is what I'm trying to explain to you. That whenever you get a question, try to convert it. This is what is referred to as a Wheatstone bridge. So in that Wheatstone bridge circuit, basically what we need to understand is that C1 by C2 should be equal. The ratio should be the same. Only when the ratios are the same, the potentials will be the same. So the central capacitor can be removed because there is no charge on it. Okay, so this is how it works. So now these 2 points can be merged together. So if these 2 points are merged together, these 2 are in parallel, these 2 are in parallel, and then they are in series. So that way also you can work it out. Or because this is removed, this is of no use, this will be in series, these two will be in series, and that combination is in parallel. So the effective capacitance is C. So the way I'm looking at it is this. So this was the circuit. Okay. So the effective capacitance of this is equal to C. This is similar to a Wheatstone bridge circuit. Okay. So that is it, most of it. So yeah, so that is it. I didn't explain to you one small thing. See, suppose this is a capacitor. I didn't explain to you breakdown of a dielectric. Suppose this is a capacitor and you have a dielectric in between. So the moment you connect it to a potential source, dipoles are generated. This is not charge, these are dipoles. Okay, so dipoles are generated. Basically what is happening is that the plus charge is on one side and then the electron cloud is shifting to the other side. So because of this electron cloud, there's a plus minus coming in and polarization takes place. Now, if this voltage keeps on increasing, so if the voltage keeps on increasing, the pull keeps on increasing, pull for charge distribution. So the pull for the positive pull charge and the negative pull on the positive and the negative for charge separation. Pull keeps on increasing for charge separation. For charge separation, the pull keeps on increasing. Now, beyond a particular voltage, the dielectric cannot tolerate the voltage. The dielectric cannot tolerate the voltage. As a result, what will happen? As a result, it breaks down. When it breaks down, electrons are released and it becomes a conductor. Handwriting is a little bad, but I've been dictating it. So that beyond a particular voltage, the dielectric cannot tolerate any more electric field. So because of that, it breaks down. When it breaks down, electrons are generated. Electrons are generated in the conduct and they start conducting. And it starts conducting. So once it starts conducting, the whole thing gets neutralized. So it ceases to exist as a capacitor. Yeah, it ceases to exist as a capacitor. Okay, so understand this. This is what is referred to as breakdown. So the reason why air conducts, is dielectric breakdown takes place. As a dielectric, it's an insulator. But when at very high potentials like that in a lightning, the air breaks down as a dielectric and then it starts conducting, and that's where it gives a path for the current, for the clouds, charge in the clouds to move. And the charge on the clouds is pretty high. It's almost like if you look at all the entire sky of the world, the charge could be somewhere like 1500 coulombs, 1500 or even more than that. So that's very, very high charge. Okay, so this is what is a dielectric, and dielectric breakdown is taking place. Okay, so if you guys understand all this, I will do one small question for you. So I have taken a capacitor. And I have charged it fully. Okay, so suppose it has 4 microfarad capacitance. And I have charged it fully to say 4 volts. My question to you, and I've removed the battery. The battery is no more there. The question to you is, if the battery has been removed, what is the work done in increasing the distance between plates to 2D. Okay, if the battery has been removed, what is the work done in increasing the distance between plates to 2D? Actually, this is a question which appeared in the NCERT exam. If the battery has been removed, what is the work done in increasing the distance between plates to 2D? So how would you approach it? Understand that initially the charge Q is equal to CV, and also understand that the energy is equal to half CV squared. Okay, Q is equal to CV and the energy stored is equal to half CV squared. Understand this. Now, if you understand this, then initial capacitance also is equal to epsilon naught A by D. Now, when you are separating the plates, the capacitance becomes equal to epsilon naught A by 2D. but the charge Q remains the same because there is no circuit. Circuit is not complete for the charge to move. So charge remains the same. So what will the new energy be? The new energy will be, I can't use half CV squared. Now I'll use half Q squared by C. So if I use half Q squared by C, it will become half C squared V squared by C. This is C by 2. Yeah. So this becomes CV squared. Initial energy is half CV squared. Final energy is CV squared. Where did that additional energy come from? Where did that additional energy come from? So that additional energy came from external source. The additional energy came from the external source. So the work done by the external source is equal to energy final minus energy initial. So that is equal to CV squared minus half CV squared, and that becomes equal to half CV squared. Okay, this keeps changing. You can't memorize this. You have to work them out. Okay, so this is the way you work out this particular question. Okay, can you make some notes? Yeah, so if you're finished, it's not over. Okay, now suppose I have the same question with the battery on. Now what will happen? So initial capacitance is equal to epsilon naught A by D. Final capacitance is equal to epsilon naught A by 2D. Initial charge Q is equal to CV. Initial energy is equal to half CV squared. Yeah. Now, final charge Q will become equal to what? CV by 2, because now there is a complete circuit. So now when you are moving it, the charge will move. So how much charge is moving? Q by 2 is moving. Q by 2 is moving through the battery. Yeah. So Q by 2 is moving through the battery. So what is the final energy stored in the battery? Half CV squared. But C has become C by 2. So this is equal to old. So I can say that it has become half of half CV squared. So that is 1 by 4th of CV squared. So actually energy stored was half CV squared. Now the energy has become half 1 by 4 CV squared. Then my question to you is, what is the work done by the external source? What is the work done by the external source? So what are you doing? You have a capacitor, then you are pulling and making sure that the plates are getting separated by 2 times the distance. In the process, I am asking you, what is the work that you have done? Okay, so these are certain things that you know. There's no great thing about all this. Now I am asking you, how will you calculate what is the work done? Okay, so let us answer. Here the work done is not final energy minus initial energy. Work done is not final energy minus. In fact, the final energy is less than the initial energy. So it is not the final. So first thing is, let us understand how much energy is lost. So do you see that initially energy was half CV squared. Finally energy is 1 by 4 CV squared. So do you see that 1 by 4 CV squared is lost? Now, is this the only thing that is lost? No. See, when you are moving this battery, when you are moving these plates on the side, a charge Q by 2 is also going across the battery. So what is the charge? What is the work done for that? So the work done for that is Q by 2 is moving against potential V. So this is equal to half CV squared. Q is equal to CV, so half CV squared. So do you see that the total energy loss is equal to 3 by 4 CV squared. The total energy loss is 3 by 4 CV squared. Okay, I'll explain this to you again. Okay, see, let's go to a new page. Let's go to new color. See, I have the plates of a capacitor and the external battery is on. Okay, when the external battery is on, initially, before I did anything, capacitance is equal to epsilon naught A by D. Energy is equal to half charge Q is equal to CV. All these things we know. Okay, then I held the two plates and then I pulled them apart with all my energy. Then the new capacitance becomes epsilon naught A by 2D. I hope you understand this why 2D, because D has now become 2D. The new energy, so do you see that this has become C by 2? So in the new energy will become half C by 2 V squared. So that is 1 by 4th of C V squared. The new charge will become C by 2 into V, C by 2 into V. That old charge of CV, now it is C by 2 into V. Do you understand that Q by 2 charge has moved through the battery? Do you understand that Q by 2 charge has moved through the battery? Okay, so if Q by 2 has moved through the battery, then what is the work done at the battery? Now you see, battery generally charge goes from plus and goes out from minus or comes into minus. But now it is going in the reverse direction. So the external agent has to do work. So if a charge Q is moved through a potential difference V, the work done is Q into V. Now the charge Q by 2 is moving through a potential V. So the work done will be this much. So Q is how much? CV. So it becomes CV squared by 2. This is the work done at the battery, not by the battery, at the battery. Now, in addition, that don't think that now the work energy is stored here to do that work. That energy cannot do this work. So that energy, there is some energy loss here also. So what is that energy loss? 1 by 4 CV squared. So now what is the total energy loss? Total energy loss is 3 by 4 CV squared. Okay, think about it. So the total energy loss is equal to 3 by 4 CV squared. Energy is lost at two places. Once inside the capacitor, once inside the battery. At the battery, the energy loss is equal to C into V, Q into V, whatever charge moves through the battery. Okay. So this is how it works. So if you guys understand all these things, what I will do, first I will show you the slides. Then I will check out if you all have any questions, I will answer them. So here I did two spheres and another charge placed at the center. Then here I goofed up this question. I'll take time to frame it. So I changed it, connected all of them, one to negative and all other. It should work. This question also should work, just that at this moment I'm feeling a little lazy to do it. Then this was the slide where we tried to work out, I tried to explain to you about this concept that if at 2 points the potential drop is the same, then if there's any capacitor between them, that capacitor will not have any charge on it. So I am trying to explain to you how to calculate the potential drop across a capacitor. or you may even say, I can also say, suppose I can ask you what is the energy stored in each, so we can understand how to work on that. So two statements made: in a closed loop, drop in potential must be equal to gain in it. Then between two equipotential points, if a capacitor is connected, there will be no charge on it. Then I explained to you the same thing and told you that, look, this is what is referred to as a Wheatstone bridge. In a Wheatstone bridge, C1 by C2 will become equal to C1 by C2. The ratio of these charges, the ratio of these capacitors must be equal to the ratio of these capacitors. Ratio of these capacitors must be equal to the ratio of these capacitors. Either way, you can look at it. Then I explained to you a circuit where it was being utilized. So here we had five capacitors, 1, 2, 3. It went this way. It went this way. Then we found out what the effective capacitance was. This was the circuit. In all these cases, C's are the same. Only when C's are the same we can do, or when the ratio, you understood the ratio C1 by C2, this ratio should be equal to this ratio, or this ratio should be equal to this ratio. Either way it will work. Then I explained to you about dielectric breakdown. This is fairly simple concept. Then I tried to ask you what is the work done in pulling the plates of a capacitor. Yeah, we can keep going on capacitors. You can keep on working with capacitors. You can keep doing on and on and on. There's no end to it. Okay, so let me take your questions if there are any. Explain the Wheatstone bridge circuit again. I'll explain. Sir, can you repeat it? What? Sir, can you teach some concepts in Tamil? இல்லப்பா எனக்கு தமிழ் தெரியாது, கொஞ்சம் கொஞ்சம் தான் தெரியும், மோஸ்ட்லி தமிழ் தெரியாது. பட் கெபாசிட்டர்ஸ் எல்லாம் தமிழ்ல யாரும் சொல்ல முடியாது. ஈவன் இன் கவர்மெண்ட் ஸ்கூல்ஸ் they will teach only in English. ஏன்னா கெபாசிட்டர்ஸ்க்கு தமிழ்ல என்ன இருக்கும் எனக்கு தெரியாது. Anyway, so there are some concepts that you want me to explain again. These are all very difficult concepts, so please don't think that you should be able to get it in one go. These things are not taught in a regular class. They are not taught. I am teaching them to you because some of you are trying for entrance. So if you are genuinely trying for entrance, you should learn it. See, suppose there is one capacitor here, there is another capacitor here, there is another capacitor here, another capacitor here, like this. Suppose this is the circuit. There is another capacitor here. Just mug it up. Suppose C1, C2, C1, C2. Do you see that this ratio is equal to this ratio? If this ratio is equal to this ratio, this point and this point will be at the same potential. A and B will be at the same potential. So if A and B are at the same potential, there is no charge on capacitor. So if there is no charge on capacitor, you can simply remove this. So if you remove this, the circuit will break down to this. So now C1, C2, C1, C2. Now you can find out the effective capacitance of this. Okay, now you can find out the effective. அதான் சொல்றேன், என்ன சொல்றேன்னா, இந்த ரேஷியோ, இந்த ரெண்டு கெபாசிட்டரோட ரேஷியோ, இந்த ரெண்டு கெபாசிட்டரோட ரேஷியோ சேமா இருந்தா you can do this. Okay, so this is a Wheatstone bridge. Either Tirpi, we will be reading it in the next chapter. When we do it in the next chapter, you will understand it better. Make notes, put in effort. Basically, the whole idea is that don't sit at home saying that ella padichiten. So that concept of ella padichiten எப்பவுமே வராது. 11th 12th எப்பவுமே வராது. உங்ககிட்ட எவ்வளவு நேரம் இருக்கோ அவ்வளவு நேரம் உட்கார்ந்து படிங்க. அப்பதான் உங்களால பண்ண முடியும். புரியுதா? சோ அது நான் படிக்க முடிச்சிட்டேன், எனக்கு எல்லாம் தெரியும், அந்த சிச்சுவேஷன் எப்பவுமே வராது. இன்னும் நிறைய இருக்கு, தெரியறதுக்கு நிறைய இருக்கு. Anyway, so this is what is a Wheatstone bridge. Okay, so